Well, this is the second lecture of CC2 in the series, and in this lecture, we will be discussing on the polar form of complex numbers. Now, so far, what we have seen that a complex number a plus ib can be represented as a point on a plane called complex plane. Now, here for a complex number z was represented by two parameters a and b, and these two parameters determine a point on a plane and as well as the complex number z. So now in the polar representation we will replace these parameters by some other two parameters. That's the conversion from Cartesian form to polar form. Okay, let's do it first. Now, as earlier we have seen this picture, point A represents the complex number Z, that means the point AB, and we join O to A, and this length O to A, sorry, excuse me, OA is called, the distance is called the modulus of the complex number Z, and it's denoted by R, and you know that this distance is actually can be calculated in terms of root over of x square plus b square. Okay, now if this angle be theta, then this distance A can also be represented in terms of this R and theta as R cos theta, right? It's simple trigonometry. And this distance B can be represented as R of sine theta, right? So now A is same as R cos theta, B is same as R sine theta. So Z can now be written in the form r cos theta plus I r sine theta. So let's take r out and the form looks like r cos theta plus I sine theta. Now note that now we have replaced A and B by two other parameters r and theta. These are the two parameters that represents complex numbers A, Z. Okay, so R is basically the modulus of the complex number Z, and theta is the angle that OA obtains with the x-axis. Now this angle theta is called the argument or amplitude, and R is, as you know, that R is called the modulus. Theta is called the amplitude. So sometimes this polar form is also called the modulus amplitude form of a complex number. So far, so good. So now let's get into the actual thing. Now note that, well, for a complex number z, the modulus r is uniquely determined. You know the formula for computing modulus, and that is root over of a square plus b square. That is root over of square of real part plus square of imaginary part. So that is not a problem. But the problem comes while measuring the angle theta that OA obtains with x-axis. So far we haven't mentioned how to measure it, and we haven't imposed any restriction. So suppose somebody, for this case, someone measures the angle theta here, though it's very tiny, plus please try to see it. If you can enlarge it, please get it enlarged, or you can see that lecture note attached with the lecture. So somebody calculates the angle theta just by going from x-axis to OA. Some other friend of yours who can move around the whole coordinate plane, a full circle 2 pi, and then go to OA. Then for him, the angle will be 2 pi plus theta. Well, so the difference between two measurement is 2 pi. Some other friend may go round twice or thrice or n times and then come to OA. So in that case, that will be a multiple of 2 pi plus theta. So as there is, although the value for cos theta and sin theta will be the same, but this angle that we are writing as a representation of a complex number, this r is unique. Okay, there is no problem with R. But while writing it, someone will write some angle here and other will write other angles here. That is not desirable, right? So that may cause a bit of a confusion. You are writing the same complex numbers but with different representations, which is not desirable. So, but the value for cos theta and sin theta will be the same. So we accumulate all such values. All these values are merely differ. They differ, as we have already seen, that they can differ only by a multiple of 2 pi. So we will accumulate them and call them ARG with A capital. They are general argument or general amplitude for the complex number Z. Well, this is one situation. Let's come to another situation. Well, in this case, say OA can be here, this point, the complex number A, the Z can be plotted here or here or here or here. Now, in this case, this alpha can be measured in this direction. Well, by the way, let me recall the thing that while measuring angle, measuring in anti-clock direction is called positive direction. That is, anti-clock direction measurement is called the positive measurement, and then we will write the angle like this. In this case, it is alpha. And if we measure in a negative direction, or the clockwise direction, that is called the negative direction, then we will write the angle as minus something. Okay. Now, in this case, this angle that OA obtains with the x-axis can be measured in positive direction and it comes up to the alpha. It can also be measured in the negative direction also, by going from here, this place, to all from x-axis all the way to here. So that will be a negative something, right? So that will be 2 pi minus some beta, say beta, say. Okay, but the fact is sine alpha is same as 2 pi minus beta. So that will be minus beta, that angle, that as it is going in the clockwise direction. So that's a minus angle, negative angle. So that angle will be represented as minus beta. So, but the value will be the same. But in sine alpha, for in the polar representation, one can write sine alpha, one can write sine of minus beta. Okay, so that is bit of a confusion. Similarly, here one can calculate in this direction or one can calculate in this direction. In this case, it is already written. One can calculate in this direction, one can calculate in this direction. So, to get rid of this confusion and to get a unique representation for a complex number Z, we have to impose. By the way, for every representation, for every such values of alpha or whichever way you calculate the angle, they are accumulated as capital ARG, as given here, capital ARG of Z. So every value of capital ARG of Z, if you put them here as the angle, then we will get the same complex number. There is no problem, but there are infinitely many. So we don't need that. That's not desirable. So we look for something called the principal value of argument of Z. Principal value is more. It's like the most elementary or the most basic value of this collection ARG of Z, the general argument of Z, the the basic one. So for to get that, to get the principal value of ARGZ, that will be denoted by small arg, or if you write amplitude, so you have to write AMP of Z with A capital, and in this case it will be AMP of Z, amplitude with A small. That's small a denotes the principal value, and to get a principal value we have to put a restriction on measurement of theta. We have to put this restriction, that measurement, whatever angle you are measuring, we will consider only the angle that lies within this range, minus pi to plus pi. will be called the principal value. And note that whatever measurement you do, only one measurement will lie within this range. Other will go either beyond minus pi or beyond plus pi. So they are members of in this the the values that coming in this part and in this part, that means below minus pi and above plus pi, are definitely members of general argument or general amplitude, but the only value that falls within this range minus pi to plus pi is called the principal value, and the value that is falling here will be considered as the value of theta that we'll write here in the polar representation. And in this case, if we put that value here with this restriction, then we will get an unique representation for z. So that will reduce, and that will discard the chance of any confusion regarding representations. So that means what? That means, this means what? For example, for this case, if z is here and y is here, this angle alpha, definitely if you measure in a positive direction, alpha is more than pi. So we will not consider, though that this alpha is a member of capital general argument, but we will not consider this alpha. We will consider this beta minus beta, which is definitely less than this. If you keep on measuring this up to from here up to this is minus pi. So this beta is less than minus pi, is sorry, greater than minus pi. So it is negative direction, so it is greater than minus pi. So it's smaller than that. The angle is lesser than that. So we will take this measurement. In this case, instead of taking this measurement, we will take this measurement. So in a nutshell, what is this restriction actually means? It means that while measuring the angle in positive direction or in negative direction, we will, or okay, first come to this. In this case, we will measure this because this is less than pi, and definitely discard this measurement in negative direction because it is smaller than minus pi. It's going beyond this line. So in other words, while measurement or measuring the angle in positive direction or in negative direction, we will not cross the negative part of the x-axis. This is the negative part of the x-axis. So wherever this A is, we will take the measurement in such a way that while measuring, we will never cross this negative part of the x-axis. Here, this measurement does not cross the negative part of the x-axis. Yes, and this measurement, this other way, the negative direction measurement definitely crosses the negative part of the x-axis, and then it comes to OA. In this case, if you take this measurement, it is crossing the negative part of the x-axis. So we will not take this one as a principal value. Instead, we will take this one. That means why? Because while taking this measurement, it is not crossing the negative part of the x-axis. In this case, we will discard this measurement because it is crossing this line. Instead, we will take this one, right? And this here we have written that whatever measurement you are taking, don't think that if we are discarding one measurement and taking another measurement means we are getting different value. No, we are getting the different thing. We are getting the same thing. But the angle that we are measuring for the principal value is, to make it a unique one, we are putting a restriction on measuring the angle by not crossing the negative part of the x-axis, or by taking only the value that falls inside minus pi to plus pi. Okay, this inequality actually means that if you keep on measuring in the positive direction, you can go up to this axis from this place 0 to 2 pi and then up to pi in this direction. And if you're measuring in a negative direction, you can measure all the way just before the negative part of x-axis. So you cannot touch negative part, because then in that case negative part minus this axis will be touched in two directions, so there will be a confusion. So we will omit that confusion also. You can touch in positive way and you can touch here, and in negative way you cannot touch here. You can reach only just before to that. All right. So far so good. That's the value that you're getting here goes in the polar representation of the complex number. Well, that's the theory. That's the convention for representing a complex number in terms of polar representation. Well, what is important is that in a polar representation, you have two quantities, two parameters. One is modulus, another one is amplitude. To be precise, the one that is coming there is the principal value of the general amplitude. That means the value that falls inside this range. Okay, so let's start with a complex number and try to represent the complex number in terms of a polar representation. Let's start with the complex number minus I. Okay, that's a definitely it's a complex number. It's a purely a complex number, and well, minus I as a point in a two-dimensional plane will be plotted here. So this is the point A where minus I is plotted, and this distance is 1, right? So how can you measure this angle? We will definitely not measure in this direction, because this measurement will cross the negative part of x-axis. So we will take this measurement in a clockwise direction, that means the negative direction, from 0 to negative part of y-axis, and this measurement will give you the value minus pi by 2. This is minus pi by 2, and we will simply not take this 3 pi by 2. That's because it's more than pi, or it's crossing this line. So we will take this value minus pi by 2 as the principal value of the argument, and the polar representation will look like what? R is 1 in this case, and cos minus pi by 2 plus I sine minus pi by 2. That's the polar representation of minus I. Okay, so let's do some more examples for minus 1 plus I, minus 1, 1 minus I, and I. And in this case, let's first we have to calculate the modulus, and in this case the modulus is root 2, is easy. And if you represent it in a polar form, then r cos theta will be your A. That means r cos theta will be your, this is the real part equal to the real part. So minus 1, and r sin theta will be your 1, because that's the imaginary part. So r cos theta is minus 1 and r sin theta is 1, and that gives cos theta is minus 1 by root 2 and sin theta is 1 by root 2. Now the only angle that satisfies these two together is 3 pi by 4, and that means going it's in the second quadrant, pi by 2 plus pi by 4. So this 3 pi by 4, and definitely 3 pi by 4 is in this, within this range. So 3 pi by 4 is the candidate for argument of z, small principal value of the argument of z, and the polar representation of minus 1 plus I will be like root over 2 cos of 3 pi by 2 plus I sine 3 pi by 2. Similarly, 1 minus I can be represented as r, well, root 2 cos minus pi by 4 plus I sine minus pi by 4. And I is represented in this format. I hope you can do it on your own. So I left it as an exercise. Now, the most common mistake that you are tempted to make is that calculating theta. See, here how we were calculating theta. we had two equations. Cos theta, we are comparing the real part. R cos theta is A, R sin theta is your B, and we are getting cos theta is as A by R and sin theta as B by R. So we had to solve these two equations for to find the value of theta, which satisfies cos theta equals to A by R and sin theta is B by R simultaneously. And it is very tempting to make this mistake. Instead of dealing with another R, let's get you are tempted to get rid of R, and you can reduce this equation as, instead of two equations, you can turn out to be, you can reduce it to a single equation, as tan theta is B by A, and theta is calculated in terms of tan inverse B by A. But that is wrong. The value that this single equation will give you may not be the argument of the principal value of the argument of the complex number z, this a plus ib. Instead, solving these two equations simultaneously definitely gives you the principal value of the argument. For example, think of this minus I plus I. In this case, we have already seen that minus 1 plus I, in this case, argument is, principal value of the argument is 3 pi by 4. But sin theta is 1 by root 2, cos theta is 1 by root 2. And if you are tempted and make the mistake, as theta is tan inverse b by a, it is tan inverse minus 1, and the value is minus of pi by 4. That's it. That's the obvious value that you will get here. And definitely that is not the argument of z. The simultaneous solution does not give this value. Okay, so that is not the argument. So don't make this mistake. While calculating the argument, you definitely solve this equation and this equation simultaneously and not the single one. Okay, now let us look at certain important result regarding polar representation. Suppose we have two non-zero complex numbers z1 and z2, and they are represented in terms of polar form or modulus amplitude form in the given format. So z1 is r1 cos theta 1 plus I sin theta 1, z2 is r2 cos theta 2 plus I sin theta 2. Here theta 1 and theta 2 definitely are the principal value of the arguments of z1 and z2. That means theta 1 lies within the range, theta 2 also lies within the range, right? And r1, r2 are the modulus of z1 and z2 respectively. Now if you take the multiplication z1 into z2, that simply a simple calculation will give you it is r1 r2 cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. Now the question is, what will be mod argument of the principal value of argument of z1 z2? Is it theta 1 plus theta 2? No, because look at the ranges. Theta 1 ranges between minus pi to plus pi, theta 2 minus pi to plus pi. So if you add them up, the range will now be minus 2 pi to plus 2 pi. So if you add these two, the value of this addition may fall here minus pi to plus minus 2 pi to minus pi to 2 pi. It may fall here also. It may not fall within this range. There are three possibilities. It may fall within this range, then it is very good. We can definitely get this addition is the modulus of addition of the argument. Individual argument will be the argument of z1 z2. If it falls here and here, we are in trouble. So but theta 1 plus theta 2 is definitely one of the general argument of z1 to z2, but not the principal value. So to illustrate this, let's look at a certain example. If z1 is this, z2 is this, and z3 is this, we have already calculated the polar forms of all these numbers. We have seen the argument of z1 is pi by 4, argument of z2 is that means I is pi by 2 and Z3 is 3 pi by 4. So Z1 into Z2, Z2 is 1 plus I, okay, 1 plus I, and Z2 into Z3 is your minus 1 minus I. Note that the argument of Z1 into Z2 is pi by 4 and argument of Z2 into Z3 is minus 3 pi by 4. This is, we haven't done that, but you can check it easily, okay, by the following the earlier method that we have used. So see, argument of Z1 Z2 is pi by 4, but and argument of Z1 plus Z2 is definitely pi by 4. So in this case, it's working fine, no problem, because pi by 4 is lying within the addition of argument of Z1 plus argument of Z2, that is lying within the range minus pi to plus pi. So in this case, they are equal. But how about this case? Z3, Z2, Z3. It is minus 3 pi by 4. But if you add argument of Z2 plus argument of Z3, that goes beyond pi. So that is not the principal value of Z2, Z3. So in this case, they differ. So in general, they are not the same. So what is the general format for getting the argument of Z1, Z2? It comes in the form of a theorem, and whatever we said right now is given in the theorem. That's the statement of the theorem. So Z1 and Z2 be two non-zero complex numbers, then argument of Z1 into Z2 will be argument of individual Z1 and Z2 plus a factor 2k pi, where k is a constant determined as k is 0 if this part, this argument of Z1 plus Z2 falls within the desired range, then we don't need any factor, they are merely the same. If they are well smaller than minus pi, then we need to add certain thing to bring it back to the desired range. So if it is less than minus pi, we need to have k to be 1. That means we have to add 2 pi to this content, to this number, to bring it within this minus pi to plus pi range. So if it is less than minus pi, we need to put k equals to 1, and if it is too big, that means bigger than pi, then we have to reduce it by 2 pi by putting k to be minus 1. Okay, so how to prove it? So the proof is more or less we have discussed. So if it is Z1 and Z2 are like this, then we have this, and Z1, Z2 we know by the simple trigonometric formulas. It looks like this, and we have already noted this fact that the theta 1 plus theta 2 ranges between minus 2 pi to plus 2 pi. Here theta 1, theta 2 are general values of argument, general argument of Z1, Z2, but not the principal value. Now there are three cases. So if we divide, as we have divided the range minus 2 pi to plus 2 pi in three ranges, minus 2 pi to minus pi, minus pi to pi, and pi to 2 pi. So it's basically the three, that is those are the three cases. Case 1, case 2, case 3. Okay. So if it is within the desired range, then there is no problem. We don't need any factor. They are the same. Okay. In this case, as we don't need, so we have to omit it. So we have to put k to be 0. So in this case, they are equal. If it is too small, that means smaller than minus pi, but greater than minus 2 pi. In this case, we need to add 2 pi to it. If you add 2 pi, you can see that then it is between 0 to pi. And that is definitely between minus pi to pi. So it comes within our desired range. And if it is too big, then we reduce it by 2 pi. And you can see if you reduce it, it becomes within our desired range minus pi to 0. That means minus pi to pi within definitely. So we put k to be minus 1 in this case. So that's the general formula for calculating argument of product of two complex numbers. So they are not that simple. It's just the summation of the individual argument, though it is very common thing to be said, but not always that is true. So we need to have another extra factor here over here, which brings it within our desired range and which goes away if already the addition is within our desired range. So that's the general theorem. And the similar thing can happen in case of division, as we have noted that z1 and z2 are not zero. So z2 is not zero, so we can very well consider z1 by z2 kind of thing. So the denominator is non-vanishing. So in this case, z1 by z2 turns out to be r1 by r2, and cos theta 1 minus theta 2 I sin theta 1 minus theta 2. So modulus of this is r1 by r2. There is no problem, but again, theta 1 minus theta 2. This can go within the range minus pi, 2 pi to plus 2 pi. Well, how it can be so small? Because if theta 1 is also negative, incidentally, then in that case it may go beyond minus pi. And if theta 2 is negative and theta 1 is positive, then it may cross pi and fall within pi to 2 pi range. So again, the proof is exactly the same, so I'm not repeating that. You can try your hand and you can write it down, and if you face any problem you can consult with me, you can contact me, you can write it in the WhatsApp group that I'm unable to write it down, then I can help you. But if you follow this proof, the writing of the proof of this theorem is exactly the same, so I hope there will be no problem. Well, so far the polar representation. We have discussed polar representation and the two vital factors, the modulus, which was discussed earlier also, and the most valuable thing, the important thing is the principal value of the argument, which comes as a theta in the representation of the polar form. Okay. Now, there are so many problems and examples and so many applications of this thing. So, a typical problem can look like this. Given they have given a complex number like this by this, and they will ask you to put it in a polar form, and they will ask you to find the value of cos of this. Well, let's do first thing first. Let's put it in a polar form. So it is z1 by z2 kind of thing. So this is your z1. So first put z1 in a polar form, and then we'll put z2, that is the denominator, in the polar form also. So if minus 1 root 3 1 I is r cos theta plus I sin theta, then r is modulus is basically 2, and it is square root of 4. Now here at this point you should note that it is easy to say that why we have taken plus 2 and not why not minus 2, because r is the modulus, and modulus means it's a distance and from origin to a point, and a distance can never be negative, so we are omitting the negative square root of 4, so we will take only this positive one. So r is 2, and then in this case cos theta will turn out to be here, comes here, so it's minus half, and sine theta as root 3 by 2. And if you solve these two equations simultaneously, the value of theta that we are getting is 2 pi by 3. And 2 pi by 3 definitely lies within our desired range of minus pi to plus pi, so that the polar representation will be like this. So if in the case of 1 plus I, we do the same method and we get the principal value of the argument as pi by 4, and this is the polar representation. And now we put them together, and if you apply the same trigonometric thing, and by rationalizing the denominator, basically what we are doing, we are rationalizing the denominator. We have noted in the last class that if we have z1 by z2, the only thing that come should do first is to rationalize the denominator, and that will solve lot of your problems. And we rationalize the denominator. Here also we are rationalizing the denominator. See, we are basically multiplying by the conjugate of the denominator. Here also we did the same thing. We multiplied it and we get this type of a representation. And note that 5 pi by 2, that's normally what we are getting here, and 5 pi by 12 is definitely falls within this range. So there is no problem with this representation, and this is the polar representation of this quotient. All right, of this ratio, sorry. Fine. And now we reduce it in terms of this point thing, a plus iv format, and which eventually gives you a representation like this. Now this and this, these two are basically two definite representation of the same complex numbers. So the real part and complex part will be same. So root 2 cos pi by 5 pi by 12 is basically the real part of here, and which gives you cos 5 pi by 12 is this value which you are asked to calculate. So this is all more or less of the basic polar representation. So in the next class we will move on to the indices, that means different powers of complex numbers, and then we will proceed towards the de Moivre's theorem of complex number, that is quite famous. And then in class lecture 4 we will be doing units, the roots of unity and roots of any complex numbers, and that's the plan of our lectures. And along with this I will be circulating another sheet with a lecture note, that is certain examples, worked out examples I have worked them out, and there is a assignment set. There are certain problems which are easy, fairly easy, and similar types of problems are solved, given as solved one also. So I would like to request you to kindly solve those assignments and mail them to our to our departmental email ID that we will be circulating with you. And I'm not hoping that you will be able to solve all the problems. That's too much of a hope. And if you can, then definitely some of you will be able to definitely do the all of them. But if you can't solve all of them, there is no problem. At least I want to see how much or how far you have tried that problem. So please also that attach that with the solution set, and I will ask you to submit within a week or so, and that's how you will be practicing the solving the problems, because uh, that is going to come in the examination. So that's all for today. Thank you very much.